Hello everyone, let us consider the second lecture that deals with the Z transform. And we are going to explain in more details the features of a Z transform. Namely, we end the last lecture by claiming that geometric series in this case we will have a geometric sequence are the fundamental feature that we are going to utilize whenever we deal with the Z transform and sequences of numbers given as a definition of the Z transform. Namely, here we have a geometric sequence and geometric sequence, it's one of the most fundamental sequences that we have in mathematics. And this is the most important expression. This expression is linked to the geometric series, which plays central role in discrete system analysis, the same way the exponential function e to the minus alpha t, which is related, this is just related to the 1 s plus alpha that we know from the continuous system representation. In other words, this geometric sequence, which is ultimately related to the geometric series, is fundamental feature of Z transform. So if we take the Z transform of A of n, geometric sequence, we have the following. K goes 0, K or I infinity, and here A Z power K. This is the canonical expression of the Z transform. It builds out that this becomes 1 A divided by Z, such that after explanation this becomes Z minus A. Okay? And this is 4 Z greater, Z complex number greater than A. In other words, if we have a complex plane, here in this area we will have a region of convergence. All of these will be a region of convergence. And this area here is just the radius of A will be the region that the system diverges. That this expression, this blue will be divergence, that this expression when k goes from 0 to infinity, this sum will essentially diverge. Okay, so we have defined that, and let us now just demonstrate simply what we mean by that and how we construct this entire story about this issue. Let us consider that we have a sequence of x I goes from 0 to infinity, and let us write 1 plus x plus x squared plus and so on. This is infinite series, and let us claim that this is 1 minus x. And this is providing that, again, x is less than 1. How we can do that? Let us, out of this expression, generate this sequence. In other words, if I have an expression to the right here, I can also generate the sequence. How we are going to do that? Okay, let us divide these two polynomials. So I'm dividing the 1 by 1 minus x. So 1 minus x goes to 1, 1. So I'm writing 1 minus x. Now that was bracket minus 1. So 1 minus 1 becomes 0. Minus minus. So this is becoming x. Now I'm saying x into 1 minus x is x minus x squared. And by doing that, we slowly build minus, this is going to be plus, so it's plus x squared. So we are slowly building this sequence. X squared plus, and so on, because x squared multiplied 1, it will be x squared here, minus x cubed, and then so on. So in this way, you see that just dividing these two polynomials, 1 by 1 minus x, we obtain this expression. Okay, now if we assume if we assume that x is equal a divided by z, we obtain the previous expression here, z minus a. Or if we assume that x is 1 by z, we obtain that z transform of unity function okay, that we saw in the last lecture is z minus 1. Okay, so all of this is essentially, in this case, a is equal 1, and all of this is essential feature of Z transform and how it is. Let us look now in another function of interest, ramp function. Say ramp function. So what is the ramp function? It's R K H. Okay? And series looks like this: 0, 1 H, 2 H, 3 H, and so on. If we would like to build the Z transform, let us quickly make how this function looks like. We will have 0 here, then 1 H, and 2 H, and 3 H, and so on. This is K, and here we have a 0, 1, 2, 3, and so on. Okay. So we want to look what is the Z transform of this function, and as previously we learned, it's just the Z transform of this R K of H is going to be nothing but summation of all of these elements that we have: 0 plus H Z minus 1 plus 2 H 0 Z minus 2 plus 3 H Z minus 3 plus, and so on. So if we just factor H outside of this expression, we will get some plus Z minus 1 plus 2 Z minus 2 plus 3 Z minus 3. Okay? And this is just all other terms. And if we even factor Z minus 1 out of this entire expression, we will obtain the following: that this is going to become 1 plus 2 Z minus 1 plus 3 Z minus 2 plus, and all other terms. Okay. Now, having this in mind, we can say that on the basis of the following knowledge, that first, 1 is 1 minus x equal 1 plus x plus x squared plus, and so on. 2, if we take derivative of upper expression with respect to dx, what do we have? So this is derivation that is going to help us to construct the closed form expression of the z transform of the ramp function. So this is 1 plus 2x plus 3x squared plus so on. So it seems like these terms, these coefficients showing up to, well, this is z minus 1, z minus 2. In other words, if we take x equal 1 by z and we substitute in the above expression, we will obtain the following: that differential d by dx of 1 minus 1x is going to become just 1 minus x squared. Okay? So this is this left term. This becomes that. Okay? And there's another term we can just copy here completely. But here, instead of x, I will write here that this is now 1 by 1 minus 1 by z, and all of this is squared. Okay? And here we are writing 1 plus 2 z minus 1 plus 3 z minus 2 plus, which so suddenly is this expression. Okay? Suddenly we have that expression. So finally, on the basis of this, we see that here we have the following: that z r kh becomes as follows. Let me move this in this direction. That z transform or r k h becomes h of z minus 1 multiplies 1 minus 1 by z squared. In other words, finally we get the h, z, and z minus 1 here squared. Okay? This is the final expression for the ramp function z transform. In the next lecture, we are going to look for the z transform exponential function, sine function, and we are going to introduce z transform of the difference equation.